Okay, I got a little object here from my kitchen to start this next question for you. Suppose suppose this little spoon here, or the handle of the spoon, needed to support some weight. And my question is, which position would it support more weight? Like this or like this? Notice it's the same object either way. Which way would it support? And as I've asked this question lots of times in classes, students always get it right. They just feel intuitively that if you have it like this rather than like this, it's going to support more weight. It's just easier to crack, although this is pretty stiff either way. That here with a heavier height to it, with more height, it's going to be harder to crack. It might be harder to balance as well, but it'll be harder to crack. And that's exactly right. And that's why when you actually figure out the equation, as scientists have done, physicists I assume, the strength of a board is equal to the width of it times the square of the height. Okay, so if you increase the if you double the width, then the strength of the board, when I say strength, the amount of weight that it can hold, will also double. But if you double the height, then this will go up 4 times. If you make the width 3 times as great, this will be 3 times. If you make the height 3 times as great, this will be 9 times the strength. Okay, so that's a fact. In fact, actually, it might be proportional, but we might as well just call it equal. It doesn't really matter. So a dentist, who's now long died, I guess, but he was a friend of the family for years, and he was part of Dentists Without Borders and things like that, so he was kind of a venerable old man. He told me once, when I first started teaching calculus, he said that he kept this in mind from his days of calculus. He kept that in mind whenever he filled a cavity of a tooth, because he just realized that the shape of it was stronger if he made it in such a way that effectively the height of the thing was greater, so that it had greater strength to it. So it's kind of cool. But anyway, for our purposes, let's assume that you are maybe building a bridge out in the woods. Maybe you've got yourself a log cabin out there, something like that, and you need a big beam to support the bridge. And so what you're going to use as the foundation for this bridge is, as I say, a big beam, which you're going to cut out of a log. So here's a log, and you're going to cut this out, and it's kind of a poorly drawn thing. But anyway, you're going to take this log and you're going to shave it so that it basically makes a rectangular beam. Okay, so it looked the same on this end. And so that's what it's going to look like. So whatever the length is, if you were to look at just the face of this beam, the face would look like this, and you're gonna shave it on all sides, so that, as I say, you're gonna have yourself a rectangle by the time you're done. So the question is, what shape should you shave? Kind of think about it again, that if you wanted the maximum area of a rectangle, the way you get a maximum area would be to make that into a square. And so that's all good, but that's not really what we want. We want the maximum strength. And so, if you think, well, we want this thing to be as tall as possible, well, that's really nice and tall. That's got a whole lot of height to it, but it's got barely any width at all. So even though, and again, this is the cross section, so this is going into the board, 20 feet or whatever it is. So the point is, this would be a beam that would be very tall, but it's not at all wide at all. Well, the width is also kind of important. So given the fact that you want it to have both width and height, but you can't have them both, as one increases, the other one decreases, what's your optimal? What's the optimal situation? So that's why I love these problems, because it's never clear what the answer is. So let's do it. So here in this case, we want to maximize the strength and we already have the formula for that. The strength is equal to the width times the square of the height. Now, what's the constraint? Well, it's not really obvious. What's the constraint? What is it that's keeping W and H from just being as big as they want? Well, think about it. Look at it. It's being shaved out of that log. Okay, that log has a certain radius to it. I'm not sure what that radius is, but it's some radius, and so why don't we go ahead and call it, give it a name. So say that the radius of this log is capital R, and so there's the radius. If we wanted to, we could say that the diameter then is 2 times R. So that's what's keeping both of these things in line, right? They can't get infinitely big because they're being shaved out of this board. So given that that log has radius R, what relationship can we say between these two? What relationship there? And maybe you can see it. This right here is W, right? And this right here is H. And this right here is 2R. And so, do you see Pythagorean's theorem there? H squared, well, let's put it right over here. H squared plus W squared is equal to the quantity 2R squared. Agreed? H squared plus W squared is equal to the quantity of 2R squared. Okay? Which, of course, is equal to 4R squared. I want to write it like that. Okay, so which one should we solve for? H or for W? Either one is easier, just as easy here. Notice that if I solve it for H squared, though, I'm just going to be able to slip that right in there for H squared. That'll be nice. If I solve it for W, then I'm going to have to take the square root, and it'll be much messier. So I'm going to solve this thing for H squared, and I'm going to get H squared is equal to 4R squared minus W squared. Agreed? And so S is equal to W times, what's H squared? 4R squared minus W squared. Okay? There is S. Let's bring it up here. I keep forgetting exactly where these cutoffs are, but basically once we have that, then we can write it all in terms of one variable here. So here's the strength. If I want to think of it as strength, now just in terms of one variable, it's going to be, if I multiply this through, it's going to be 4R squared W minus W cubed. Now, you may say, wait a second, that still has 2 variables in it. This one had W and H, this one has W and R. Is that a problem? No, it's not a problem. You've picked your board. You've picked your log. Okay? You've got a log there that you're working with. That log has a radius of R. So that's fixed. That's not it. We were calling it R because we don't know what it happens to be, but it's nothing that can change, right? That's nothing that can change. That's not a variable. You're not once you have your log, you get to choose whether you want the board to be like this or whether you want the board to be like this. I mean, you have all sorts of choices for W and for H, but you don't have a choice for R. That stays the same. So we made progress, right? We still just have one variable there. That's a constant. Treat it like a 5 or anything else. Okay? So now we can go ahead and take the derivative. And so here we go. S prime of W is equal to, and again, don't lose sight of what you're doing. We've got something here that, if you look at the extremes, if H is really close to 0, you've got something that looks like this, which is not going to hold any weight. Or if the width is really, really small, you're going to have something like this. if either one of these things goes to 0, you're going to have basically no strength there. So those extremes are no good. So the maximum must occur in between. So this thing must go up and come back down. And wherever it starts coming back down, we want to find that maximum. And this is W right here. This is the strength. We want to find that maximum, and so that's going to be where the derivative is 0. So never lose sight of that. It always, it's really depressing when I teach all this stuff, and then people, maybe students, will take the final test and they will set the function equal to 0 or whatever else, and it shows no, they haven't internalized the idea. So you want to find out where that maximum is. That maximum occurs where the derivative is equal to 0. So we first take the derivative. This is a constant times w, so it's going to be 4r squared minus the derivative of this is going to be 3w squared. Agreed? So there it is. Now we set that equal to 0. And we can bring this over. I'll just leave it. And so W is going to be what? 2r over the square root of 3 if you solve it for W. Okay, so there's W. Let's see, should we find out what H is, just so we have it? What's our relationship? We know that these two things together have to add up to this. So here's W. If I square W, I'm going to get, let's write it like this. W squared plus H squared is equal to 4 capital R squared. And now if I square this, I'm going to get 4r squared over 3 plus h squared is equal to 4r squared. H squared is equal to what? Let's see, how many, you have a bunch of r squareds here. How many do you have? You have 4 thirds here. This is 12 thirds. 12 thirds minus 4 thirds is going to be 8 thirds. It's going to be 8 thirds. And so h is equal to 2 times the square root of 2 over square root of 3r. So what's the relationship between W and H? It looks like H is square root of 2 times greater than W, which makes sense. I mean, you want it to be taller than it is wide, because the tallness, the height of it makes more of a difference, right? Makes more of a difference to the strength. So there it is, right there. So there's the dimensions, and so there's a really nice practical problem. If you had to shave, you had yourself some sort of a log, and you had to shave it in order to get as strong of a beam as possible. That's the way you'd want to do it. So pretty cool. 2 more problems. Actually 3 more, and these are all problems that I've actually made up all on my own. 2 of them have been published. I've become famous for one of them in particular, and then one other as well. So some good stuff coming up. It's kind of fun. We'll see it.